It's my pleasure to announce our speaker, Amir Mohammadi from the University. Amir works in several areas of mathematics, in ergodic theory, in dynamical systems, and in the applications and links to number theory. And today Amir will talk about finitary analysis in homogeneous spaces.
Thanks very much for the invitation. It's great to give this talk, and thank you for the introduction. Yeah, this talk is an outlier compared to the general theme of this conference, so treat it as an entertainment. I want to start with actually an application, even though it was dropped out of the title, and then somehow motivated with this application, I want to go back to homogeneous dynamics. So I want to study some equidistribution problem arising from number theory. So the space is going to be the space of positive definite quadratic forms. So I have Rn, I look at the space of all positive definite quadratic forms on it, but not all of them as they are. I want some sort of an equivalence relation on them. So I want the two forms that are a multiple of each other, I will identify them. And if they are equivalent over Z to each other, I will also identify them. So the space of quadratic forms modulo this equivalent relation is going to be this Qn. Of course, GLNR acts on the space of quadratic forms. And the action is, well, the familiar action. The identity matrix, if you fix the identity matrix, every positive definite form can be written as GG transpose for some G in GLNR, and that's the action. So there's a transitive action of GLNR on this space. And because I am identifying two forms that are equivalent modulo this relation, and GLNR acts, if I just was looking at the space Qn tilde, then I would have GLNR modulo the stabilizer of the standard form, GLNR mod PON. And because of these identifications, two forms that are the same under GLNR I'm identifying. So I get this nice space PGLNR modeled out by PGLNZ from one side and the stabilizer of the standard form in the other side. So this is the space Qn. I can naturally identify it. This space is familiar to number theorists, at least the case n equals 2. This is where life happens. So it's not a compact space, but it carries a natural finite measure. And I have drawn the fundamental domain for n equals 2. And I want to study some equidistribution problem in this space. So I need to give you some points in this space and then ask whether they are equidistributed in it or not. And how are these points constructed? These points, well, they're constructed also in a number theoretic context. So I give myself some positive definite integral form. And I look at, if this genus is something you are allergic to, just look at the discriminant notice. Look at locus. Look at all the forms that they have the same discriminant, but this is a finer question. So I think this is one conference that I'm allowed to define this and nobody will be offended. So I look at genus of a form, which is the set of all integral forms which are locally equivalent to my form, but I don't know whether they are globally equivalent or not. So locally equivalent meaning that over R they are equivalent, and over all the p-adics, ZPs, they are equivalent. So there's a n by n real matrix that sends B to B prime, and for every P, an n by n matrix in GLN-ZP that sends B to B prime. This is a set of quadratic forms, and basically what I'm saying is that the two forms are locally equivalent, and of course there's a usual game of whether you have a local global principle, whether you can have local equivalence implies global equivalence, which, okay, for positive definite forms, we know that this is not true. Genus is generally large. So just some remarks before I mod out this genus by the equivalent relation and get finitely many points. Of course, because I have equivalence over all R and p-adics, these forms are rationally equivalent. The question I'm looking at is Z equivalence, which is much finer than rational equivalence. So I could replace this are over here by Q, but that's okay. This is well known. And you may wonder what's somehow simple examples of forms that are somehow rationally equivalent, but not globally equivalent. So these are two forms. Integral, they are equivalent over all ZPs over R, but they are not integrally equivalent. So this genus, we expected to have many points in it for positive definite form. Unlike indefinite forms where, okay, if you replace genus by spin genus, then you are looking at a simply connected group, and simply connected groups, they have class number 1. So it's this spin genus is going to be 1. But the genus for a quadratic form, for a positive definite quadratic form, usually has many points. And another remark is that two forms that are in the same genus, of course, they have the same determinant because you have equivalent over all ZPs. And this is basically saying that determinant of the two forms, which is going to be a rational number, is going to be a unit over all PIDs. So that's what it is. And now I finally get the points I was after. I take this genus of a form and mod it out by this equivalence relation. I get finitely many points in Q1. And the question is, do they become equidistributed? So I've got myself finitely many points in the space of quadratic forms. Do they become equidistributed? And well, let me right away state the theorem. The theorem is that they do. They do, and they actually become equidistributed in a quantitative fashion. This is already now a few years old. Joint work with Manfred Einzelder, Margulis, and Venkatesh, that if n is bigger than or equal to 3, then the genus of a form becomes equidistributed with respect to this natural measure that I said lives on the space, and the error rate is polynomial in genus. So you have this equidistribution. Now, some remarks before I somehow switch gear in a sense and talk about what goes into this proof, and then somehow what has happened since this theorem. Like I said, this is already a few years old. Okay, so case n equals 2, this is classical. This was proved by Bill Duke using a breakthrough result of Ivanić. The problem is quite different in dimension 2 and the higher dimension. Basically, if I want to describe this in one sentence, the reason is that the isometry group in dimension 2 is commutative, is a torus. The isometry group in higher dimension, this is a semisimple group. It's got a complicated structure. So the problem simplifies as dimension grows. This is true, but this problem in dimensions 3 and 4 actually is kind of difficult. If you don't care about this rate, and you're content with just the fact that this sum goes to that integral without any rate, if you let the dimension be bigger than or equal to 5, then this can be proved using softer techniques. There is work of Grodnik and O that you can use to prove this. But in dimensions 3 and 4, even if you don't care about the rate and you just want to have equidistribution in a qualitative form, there is no other way to go about this unless you assume some sort of splitting condition, similar to what Linnik and Skubenko had. So Linnik and Skubenko, before work of Duke, studied this case of n equals 2, but they had a condition on discriminant. Discriminant had to be residue mod some p or some fixed prime that the discriminants are residue mod. This is what they needed, and this is to somehow get some action of a p-adic torus or something in modern language. You can say it that way. In this case, cases of 3 and 4, also, if you don't care about rate and you just want equidistribution, you need to restrict yourself without using the quantitative analysis. Then you will need to restrict yourself to those forms that over some p-adic, they're not compact. They give you some. There is some splitting condition. But if you really want to not have this type of splitting condition and have a result like Duke and not even care about the rate in dimensions 3 and 4, the only way to get it is to go through the quantitative analysis. You can't somehow use the softer results. So what I want to do now is to somehow maybe, like I said, change gear and leave this space of quadratic forms, go talk about some problems in homogeneous dynamics, and we'll return to this after I've set up the stage. So now, dynamical approach, I want to start with this fundamental theorem of Ratner, which has had many applications in number theory, actually, and also geometry. And this is a rigidity problem. So suppose you have a connected Lie group, take your favorite one, SLNR. And take a lattice inside it. This is a discrete subgroup which has finite co-volume. Again, everybody's favorite example, SLNZ. So SLNZ inside SLNR, and take a group inside G, which is acting on G mod gamma. So I want to understand orbits of this group acting on G mod gamma, and I want to understand orbit of every point. It is crucial that I understand orbits of every point, and not only almost every point or most points in some measure theoretic or topological sense. And this is crucial for applications, because when you want to apply such a result in number theorists, I mean, there's Z. You want to understand statements about Zn. And if you are looking at SLNR mod SLNZ, this is, you can think of this as a space of lattices and in Rn. And there also, I want to understand something about one point. So it's very crucial that I want to understand orbit of every point. And fundamental theorem of Ratner says that we do understand this if the group that you're acting by is generated by unipotents. Unipotent matrices are these matrices that they have all their complex eigenvalue equal. Unipotent elements are these elements that they have all their complex eigenvalue equal 1, and a group is unipotent if it's generated by unipotent elements. So for example, if you have SLNR, SLNZ, you can take your group W to be either SL2R or some or the strictly upper triangular subgroup of SL2R. And Ratner says that orbit of every point under such a group is a nice submanifold. There is no fractal behavior. And these submanifolds are quite specific. They actually arise as orbit of intermediate groups. So there is an intermediate group which has a periodic orbit. It has a closed orbit. And then this orbit closure precisely equals Lx. Okay, so this is, it's quite a deep result. And of course, this condition that your group is generated by unipotents is essential. This theorem is false if you replace W by a one-parameter diagonal subgroup. Diagonal actions, one-parameter diagonal actions, they present no rigidity. Essentially, you have positive entropy. You have it's a Bernoulli action. You can have orbit closures that have fractal behavior. So it is absolutely essential that you have these unipotent subgroups to work with, at least in the work of Ratner. So there's some more recent work which I will mention, but definitely you need some condition on the acting. So this is somehow the type of theorem that I want to discuss, and I also want to relate this genus problem to a question of this nature. Now, some historic remark before this work of Ratner. Special cases of this problem were studied by Margulis and Danny Margulis in the context of Oppenheim conjecture. So Margulis proved the Oppenheim conjecture by proving the special case of this, where you look at SL3R mod SL3Z, and you look at the action of the isometry group SO21. And there were generalizations by Danny and Margulis. Also, Nimish Shah, in some topological context and more geometric, considered the rank 1 group SON1 mod gamma and studied the unipotent things. This actually came out roughly the same time as Ratner's theorem. So that's an important remark and an important link between this problem and number theory, the Oppenheim conjecture about quadratic forms. And this was the solution at for dimension 3. Still, there is no non-dynamical proof. So the only proof existing is using dynamics. But actually, prior to these works, a classical case of study is when your group W, the acting group W, is big, and this is the notion of horospherical subgroup. I will return to this because this is again a case that has linked to representation theory and number theory. In these cases, somehow the problem is easier, and they were studied already by Hedlund in the 30s. And Furstenberg, Veach, and Danny generalized this. And the picture in here can be drawn as this. So the theorem I stated said that orbit closures are very nice. So in the case that you're looking at SL2R, and the group that you're acting with is the upper triangular group, the strictly upper triangular group, these are the horocycle flows on the tangent bundle of surfaces. So you either have a compact surface or a surface with some cusp. If you have a compact surface, then basically what Hedlund proved is that every orbit is dense. So there's a minimality. Every horocycle you take, you project it to your manifold, you get a dense set. When there is cusp, of course, it could be that you have a periodic horocycle, but what Hedlund again proved is that that's the only possibility apart from density. Either you're dense or there is a periodic horocycle that this is just sitting on top of the periodic horocycle. So there's perfect rigidity. Either you have density or there is some geometric or algebraic obstruction that's preventing density. There's no chaos going on. And like I said, this is very different from the case of geodesics. If you look at the geodesic up here and project it, then the only limitations are dimension. You can have orbit closures that have Hausdorff dimension, any Hausdorff dimension between 1 and 2. So it's very different. Now, I will be focusing on the case of groups generated by unipotents, but it should be mentioned that there has been fundamental work, again, allowing other choices of W. If you take W to be not one-dimensional, but multi-dimensional diagonal group, then this is related to Furstenberg's famous times 2 times 3 problem and Littlewood conjecture in the Diophantine approximation, which, fundamental spectacular progress was done by Ketog, Einzidler, and Lindenstrauss, where they show that the set of exceptions has Hausdorff dimension 0 by studying the action of diagonal group on SL3R mod SL3Z. And you might want to leave the realm of connected groups and look at maybe some Zariski dense subgroup acting on G mod gamma. And these also were studied by Morgan, Foreman, Lindenstrauss, and Moses. This work I will return to because this is actually a quantitative work. And Benoit Kahn generalized this to G mod gamma. Ideas developed by Benoit Kahn actually found applications beyond the homogeneous setting for the SL2R action on the modular space of compact Riemann surfaces. This was the breakthrough result of Eskin Mirzakhani and a follow-up orbit closure joint with them. Maybe last remark I want to make, I will focus on the case that gamma is finite volume, but this is again a number theory seminar, and I'm sure people are fond of thin groups as introduced by the terminology introduced by Sarnak. So you might somehow want to allow gammas which have infinite co-volume. And in this case, also some work has been done in geometric context, joint with Kurt McMullen and Hio, and some follow-up works of Hio and Benoit Hio and her student Lee. But the theorem I stated as a motivation had a rate. These theorems, as fundamental as they are, with the exception of this, none of them has a rate. And actually, it's quite difficult to try and write a rate. So there is somehow, Ratner's theorem tells you behavior of every orbit, but it won't tell you how long you need to wait to visit epsilon neighborhood of a point. And often in applications, you want to have such estimates. You want to know the smallest solution to some Diophantine inequality. And so dynamical approach can give you existence of this approximation, but we might also want to have a rate. That being said, it's quite difficult to actually find these rates. Already for irrational rotation of a circle, we see that the angle of rotation, how irrational it is, this is important. I wanted to write an example which is continuous, which is connected example. So take the two torus, maybe leave one torus, go to two torus, and then you look at the line. Now, depending on what the slope of this line is, somehow when you take the quotient and you go to the torus, you need to wait probably a long time to see that it becomes equidistributed. So if you have a line whose slope is epsilon and you only catch the piece of the orbit, which is like 1/2 times epsilon, then you have only filled up half the torus. And why is this? So what's responsible for this is this closed subtorus. Somehow you're too close to this closed subtorus, and this algebraic Diophantine property somehow prevents you from going everywhere in the space unless you wait long enough. So it is a delicate problem, and the works in this direction are somehow less conclusive than the non-quantitative results that I mentioned. So I want to give a brief history of what is known. The first case is the case that the group G that I said was a Lie group, this itself is a unipotent group. So this was done by Green and Tao, and already this work was mentioned actually in the first talk in this conference. So they prove quantitative density, quantitative equidistribution with very good rates, with polynomial rates. And this is used to show somehow independence from Mobius later. So these Neal sequences, etc., they are one of the inputs for this orthogonality, this paper where they prove effective version of Ratner for the case that the ambient group is unipotent. But if you don't want the ambient group to be unipotent, the approach that is developed by Green and Tao is not going to help, because somehow the proof is an inductive proof using nilpotency degree, etc., etc. It's not a proof that can generalize to semisimple groups. So the case of semisimple groups, also some progress has been made. If you look at the quantitative versions of the Oppenheim conjecture, this was done by Lindenstrauss and Margulis. The rate they obtain is not the best possible. One would ideally like to have a polynomial error rate, but they get something which is polylog. But still, it's a great achievement. So you have this is a special case of what they prove. Suppose you have an indefinite non-degenerate ternary form whose coefficients are algebraic numbers, but the form is not a multiple of an integral form. Then you give me epsilon, then I can find you or they can find you a vector v in Z3 whose norm is not too big. It's explicit in terms of epsilon. So it is exponential of 1 over some power of epsilon. This n is absolute. And how small epsilon should be, so this actually is valid, depends explicitly on the height of the coefficients and the degree of the coefficient, so that Q of B is less than epsilon. So they can give you explicit bound on the solution to this Diophantine question. This, like I said, so the argument here is to somehow effectivize and generalize ideas developed by Margulis. If you just try to effectivize Margulis's proof, okay, it will take many, many pages, but the rate you're going to get is going to be super exponential here. So you're going to have x of 1 over epsilon. There is an important input in this work, which is a combinatorial lemma that saves one exponent or one log, depending on how you want to think about it. So following these general ideas, somehow trying to effectivize existing proofs, this is, like I said, it's a tedious work, difficult, and the rates you obtain are quite poor. This is an ongoing work joint with Lindenstrauss, Margulis, and Shaw, where we proved a complete analog of the statement that I wrote, but with the rate unfortunately is rather poor. It's an iteration of log where the number of logs depends on the mesh. But for several applications, you are interested in rates which are good in the sense that they are polynomial. What is known in terms of polynomial rates? Not much. The short answer is not much. Or rather, the short answer was essentially nothing beyond two very important examples up to a year ago. So there's one case that is rather well understood, and this is the action of horospherical groups that I mentioned there. These are big subgroups in your ambient space, because if you look at their normalizer, for example, the quotient is compact. These are radicals, unipotent radicals of parabolic subgroups. They are big unipotent. And tools from representation theory and number theory are available to study these, and harmonic analysis are available to study these, and they have been studied throughout. So Margoulis's thesis, Sarnak's thesis, later Berger and Duke, Rudnick, Sarnak, Eskin, McMullen, the list is there, and you can see. So we have a pretty complete picture. Strombergson took this step further and looked at the case that you look at semi-direct product. So you look at maybe SL2R, semi-direct product R2, modeled out by SL2Z, semi-direct product Z2, and then you take a group, which is the upper triangular subgroup in here. So this is not horospheric. Analysis here is substantially more complicated, but it is related to horosphere, and he manages to prove effective versions for these groups. Now, another significant work is the work of Bourgain, Forman, Lunenstrauss, and Moses, which I mentioned. This is about random walks on the torus. So you look at toral automorphisms, and you have random walk by some big subgroup in the sense that it's risky dense, it's some extra conditions, and then they prove equidistribution with a rate for these actions. This is a work that I will return to in a couple of slides. The ideas here are somehow they use additive combinatorics. It's quite a novel technique. One other important case, which goes back already more than 10 years, and this is, I think, 4 or 5 years, is when you look at periodic orbits of semisimple groups and you assume your gamma to be a congruent subgroup. Here, automorphic forms somehow, automorphic techniques are, not automorphic technique, we don't use automorphic techniques, but some input from the theorem of automorphic forms is crucially used to give effective results. And this crucial input is the uniform spectrum. Again, property tau plus L and others is used to get effective equidistribution for periodic orbits. And this is exactly what is used in the proof of the Genus problem. So I don't want to state this, but I want to go back to Genus and see how you can apply this thing to Genus. So again, let's give ourselves a quadratic form. I have the spin group of the quadratic form. This one has a natural map to PGLN. I have genus of B sitting in Qn. In dimension 2, genus has a group structure. Somehow this is nice, but in higher dimension, there is no group structure. You can't compose to integral forms. However, genus still has some hidden symmetries. These hidden symmetries are given as a cover. So you have a covering of this genus by a big homogeneous set. I could have, rather than using Adels here, I could have just taken one prime, but okay, again, this is one place that I'm allowed to write Adel without being apologetic. So I look at the homogeneous space, PGLN of Adels, mod out by PGLN Q. This one projects to PGLN R modulo PGLN. Remember that this set was PGLN R modulo PGLN Z, and from this side I have PON. So this definitely covers that space, and then I have this homogeneous space of the spin group obtained by the spin group, and this element G is the thing you think it is. So it's got an infinity component and identity everywhere else. And this infinity component is the thing that conjugates my form B to the standard form. So this is the element. I look at this quotient and I push it forward with this element G. This will cover my genus. Now, the theorem we prove is an equidistribution result for the upper line. So this set becomes equidistributed with respect to the Haar measure on this quotient, and this will imply the theorem that I want. So it's a theorem about adelic periods. You look at a quotient of a semisimple group, and you look at adelic periods in there. And what we show is that adelic periods are effectively distributed with respect to the volume. So the volume of this you need to define. There is some arithmetic complexity of this, and that is polynomially related to number of points in genus. So this is how the theorem is proved. We prove the first line and obtain the second line. That the first line is equidistributed. We obtain this. So like I said, up to less than a year ago, this was basically the story. So there are some somewhat weak bounds for general problem. And if you have the settings that either you have a horosphere or you have a periodic orbit, then there are inputs you can use to get polynomially good bounds. But these techniques are somehow, they won't apply to general orbits. The fact that I have a periodic orbit is extremely important here because uniform spectral gap of these periodic orbits is used crucially. And the fact that you have horosphere is just somehow a nature of the arguments here. So if you want to understand general orbits in semisimple quotients, this is a difficult problem, and you want polynomial bounds. This is a difficult problem. So I want to now somehow say what has happened in the past year. And this is not in the generality that Ratner's theorem was. It's a very specific example, but even this took quite a bit of time. So I'm going to be very concrete, a case of two groups. Either think about SL2C or product of two SL2s. And take gamma to be a lattice, and a subgroup of this, which is the one you think, either SL2R inside SL2C or the irreducible copy of SL2R inside the product. So it's sitting diagonally inside the product. You can ignore this. The theorem I'm going to state is about this P, but just think about H itself. I look at G mod gamma. I look at an orbit of H, which I don't know it's periodic. So it's a general orbit. Do I know that it becomes effectively dense with a polynomial error rate? Problems of this kind also have quite deep number theoretic applications. Waxall used the case of SL2QP times SL2QP to prove something about special values of L functions. So they will eventually have number theoretic applications, though the application I will mention today is more on the geometric nature. But okay, so this is the question. I have this subgroup SL2R sitting inside SL2C. Can I say something about the orbit? And the answer is yes. So there is a polynomially effective density result in this setting. This is a mouthful, but basically at the first sight, what the theorem is saying is that either there is an explicit algebraic obstruction of low complexity that prevents density, or you're this. So this phenomena should be a familiar phenomenon. Either there is an explicit reason of low complexity that is preventing your orbit from becoming dense, or you have density with a rate that's actually polynomial in the parameter. So now the statement, maybe I should read it once. So I assume gamma to be an arithmetic lattice, and I give myself a parameter which is trying to control the complexity of the obstructions and a point. Then, so long as the parameter t is large enough, the orbit of this point becomes dense in the space. If X is compact, you can ignore this index. This is X. If X is not compact, I need to cut it at some point. It's a finite piece of the orbit. I couldn't possibly hope to go everywhere in the space, so I need to cut it, and this is what this subscript here is. If you are happy with assuming that X is compact, you can ignore that. So every point in this compact piece is close to some point along the orbit, or my point was close to some periodic orbit of low complexity. This is the theorem. Now the proof is somewhat involved. It has flavors similar to the breakthrough works of Gambor-Sarnak and the previous work Gambor-Jacobson-Sarnak on the random walks. So the family of Cayley graphs are expanders, and also the work that I mentioned of Borgan, Forman, Linder, Strauss, and Moses. Maybe I would briefly mention the 3 steps and then go to the application. So there are 3 phases of the argument. There is an initial randomness. So we want to show that points have some initial disjoint, some initial isolation from each other. This is, again, a phenomenon that should be familiar to the audience here. If you have 2 rational points of not very big denominators, they are far from each other. So this is this notion of initial randomness. So using the fact that gamma is arithmetic, we can show that points cannot get too close to each other along this. But this exponent so somehow I apply ball of radius t to my point, and then I want to have points far from each other. What I can show is that many points are distance t to minus d. This d is huge, is very far from what you want to get equidistribution. So this is a very huge number. And the goal is to bring this d down to a range where you can get some useful information. And this is this bootstrapping phase, that we try to use some sort of a random walk to decrease this d by passing to a different scale, improve this dimension at coarser scales. Here we use these techniques of Margulis functions, which were introduced by Margulis, Eskin, and Moses in their work on quantitative versions of, on basically equidistribution versions of Oppenheim conjecture. So we use this to bootstrap this dimension to a dimension that is close to optimal dimension. Then we use 2 tools. One of them is something from a tool from incident geometry, work of Wolf and Schlag on Kakeya problem. Somehow we need to project this dimension that we have got, which is in the complement of SL2R. We need to project it into a desirable direction. For this, we need a projection theorem, which we use work of Schlag and Wolf on Kakeya problem to prove this. This is different Kakeya problem than the one that it's not about lines, it's about maybe circles or parabolas. So you have a family of parabolas in R2, and then you want to know that there is big dimension. And finally, after we have projected this to a direction that we like, we use some argument due to Venkatesh, I think in his thesis perhaps, to somehow show effective density. This one uses exponential decay of correlation, but only for the ambient space, which is always there. It's very different from uniform spectral gap. Uniform spectral gap that I mentioned, this was about the periodic intermediate orbit. This is decay of correlations for the ambient space. You always have it. Okay, so now maybe I want to mention some application. So I said periodic orbits were studied by Einzidler, Margulis, Venkatesh, and a follow-up work. In there, of course, the assumption was that gamma is a congruence lattice. The work we have here will also tell you something about periodic orbits in this particular case. This part, for periodic orbits, you don't need to assume gamma is arithmetic. As you see in the scheme that I said, arithmeticity was used to get some sort of initial randomness. Periodic orbits themselves are Diophantine. Just like rational numbers, You can't have two rational numbers too close to each other. Denominator is an issue. So periodic orbits are themselves isolated. So the rest of the argument you can apply and get something about periodic orbits. This has application to some finiteness theorem, the case of hyperbolic manifolds. So there are these hyperbolic manifolds in every dimension, but I am interested in dimension 3, constructed by Gromov and Piasecki-Shapiro. These are these hybrid manifolds. So of course, there is Margulis's arithmeticity theorem that tells you if you give me SLN-R n bigger than 2, then every lattice is arithmetic. But SL2R has many, many non-arithmetic lattices. There is a whole Tauchmiller space for it. Same is true for SON1 for all n's. There is no Tauchmiller space for it, but there are non-arithmetic lattices. And explicit examples were constructed by Gromov and Piasecki-Shapiro. So the construction is this picture. You take two arithmetic manifolds, M1 and M2, but you assume that the arithmetic structure on them are not related to each other. So they are not commensurable. So this one comes from Q join root 2, the other one comes from Q join root 3. And assume that you have some closed submanifold, closed surface inside. Then you cut these two manifolds open, and you assume that these two are the same surface. So they are two isometric surfaces. You cut the two manifolds open, and then you glue one piece of this to the other piece of the other. This gives you a hyperbolic 3 manifold, and the fundamental group here is now non-arithmetic. So if you don't like pictures, which I noticed actually no other talk had pictures. I have some pictures. So this is how you construct. So you give yourself two manifolds, M1 and M2, 3 manifolds, and you assume that each of them has some submanifold with boundary whose fundamental group is Zariski dense in SO31. And then the boundaries are isomorphic. You cut them open and you reglue. What you get is a hyperbolic 3 manifold. And the fundamental group is not arithmetic because these two groups, they both are sitting in your arithmetic, in the fundamental group. And for arithmetic groups, you couldn't have Zariski dense groups that are coming from different structures. You can't have it for arithmetic groups. The question is, okay, if you give me one of these, how many totally geodesic submanifolds does this have? This is related to a question that was asked by Alan Reed and Kurt McMullen about whether this is a recipe for arithmeticity of manifolds, which was recently proved by Margulis and myself, and also Bader, Fisher, Miller, and Stover generalized it to all dimensions. So for these particular cases, we can actually bound how many totally geodesic subplanes such a manifold can have. So basically, you give me a manifold, a Gromov-Piasecki-Shapiro manifold. In terms of the geometry of this manifold, I can bound the number of totally geodesic planes that you have. So there is finitely many. This was actually proved by an earlier work of Fisher, Lafond, Miller, and Stover. This predates this other result that I mentioned, but now we can actually bound how many there are. And the bounds depend on coarse properties of the manifold. Okay, so there's the volume, there's area of this surface that you glued along, and basically spectral gap of the ambient manifold. So there are very explicit properties. The argument for this, well, uses the EQ distribution that I mentioned, and some nice fact about when you have a totally geodesic plane in such a manifold, in a Gromov-Piasecki-Shapiro manifold in M, then this manifold, this totally geodesic plane has to intersect sigma orthogonally. This is what I meant by angular rigidity. There is a very restricted way that a totally geodesic plane can intersect this sigma. So this is sigma. Totally geodesic plane needs to come and intersect this orthogonally. Using this and the EQ distribution result, that's the density result that I mentioned, we can bound how complicated can this be. We can bound the volume of this, and then if you bound the volume, then you have a bound on the number of planes, again, based on the same principle that periodic orbits repel each other. You can't have periodic orbits that they get very close to each other.
It might be a naive question. So when we're talking about these rates of convergence for equidistribution, do we ever have any idea if they are optimal bounds?
That's a great question. Unfortunately, these methods give very poor bounds. So this work I mentioned actually here. So this work gives a different proof of Clausel's part for property tau. So if you assume Selberg and you assume Jacquet-Langlands, so for groups of type A1, then we can use property T to prove Clausel's property tau. But the bound we get are much worse than what Clausel gets. And this is true for essentially all these results in here. The bounds you get are quite a bit worse.
Actually, I have a question, kind of a very generic question. Yesterday, Camille gave a talk about the Glasner problem, which feels to be of the same spirit. You also have an action of some set of matrices, and you want this orbit to be dense.
That's the remark. Yeah, this Bougan-Fuhrmann interstrasmosis can be applied to Glasner property to study it. So I think you can also give quantitative results, because that's what I sort of mentioned in my talk. We wanted some more quantitative properties for this Glasner property. I guess, you know, Igor, in our recent work, we're interested in like polynomial orbits, so like quasi inequality was useful. But for, you know, to apply these techniques, you need some quantitative properties on like the orbits of rational points. Like if it has large denominator, does it equidistribute quickly? And I think Bougan-Fuhrmann interstrasmosis gives you some information on that as well.
That's right. Yeah, I think it does.
And so, just out of curiosity, delta in your result, which you formulated at the very beginning.
Yes.
What is this?
It's a very small number. When I was a bit younger, I tried to write one of these deltas for the case of SL3R and SO21. And what I got is 10 to the minus 8 or something.
Okay.
And this is going to be even smaller.
Let's thank the speaker again.
Thank you.